Hi guys, and welcome to the introduction video to the law of sines. So far in trigonometry, we've looked at a variety of trig problems, whether they're based on right triangle trig, where we are solving for an unknown side or angle of a right triangle, or whether it's functional trig and we're graphing sine, cosine, tangent, cotangent, cosecant, secant, and using the unit circle to get us some help there. What we're going to be really focusing on in this chapter are applications of trigonometry. And the first of those is something called the law of sines. The law of sines lets us apply what we know about trigonometry to any triangle and begins to help us solve for the sides and angles of any triangle that we don't know those values for. In today's mini lecture, we're going to show why this works through a short proof, and then do a couple examples of law of sine problems. We know, for instance, in the triangle shown here, where I know it's a right triangle with a 30-degree angle, I could even fill in 60 degrees up top, that I can pretty quickly solve this triangle even if I don't recognize it as a 30, 60, 90 right triangle by using the sine function, recognizing that the sine of 30 degrees equals the ratio of the opposite side to the hypotenuse, x over 7. Sine of 30 is going to equal 1/2. If you don't know your unit circle trig, feel free to use a calculator for that. Make sure that your mode is set in degree, and then type in sine 30 and press enter. That'll give you 0.5. So if sine of 30 equals 1/2 and 1/2 equals x over 7, I can multiply both sides by 7 pretty quickly to get x equal to 3.5. Okay, so right triangles really aren't the problem. We've got a lot of practice with them. You've done some Pythagorizing since you were studying geometry for the first time. Where things get messy is in oblique triangles. Now, an oblique triangle is any triangle that doesn't have a right angle. And I've drawn two of them. I drew an acute and an obtuse oblique triangle. And within these, we don't have a good way to solve for the entire triangle like we do with right triangles. A note about conventions in math. If you haven't noticed it so far, here's something that we typically do in mathematics. We label angles with uppercase letters. In both of these cases, I used A, B, and C. And we're going to use lowercase letters for the lengths within these triangles. The convention is to use the lowercase a opposite the uppercase angle A. So side BC has a length of A. Side BC is opposite angle A. And that really is going to come into play when we begin to take a look at the law of sines. So the law of sines is a way for us to solve oblique triangles. And let's draw one of these. I drew a acute case of an oblique triangle. If you'd like to see more of this proof done out, including a complete proof for this, you can check out the video a couple pages after this. This is just an introduction to the law of sines, so I didn't want to bog that down. If I write the relationship for sine A, I can recognize that in this small triangle on the left side of the interior, the opposite side is h and the hypotenuse is b. So sine of A I can write as h opposite over hypotenuse b. Now I know it gets a little bit confusing using h for both hypotenuse, which we usually do, and for the height of this triangle, but bear with me for a moment. The sine of angle B is going to be the opposite, once again, it's the h. Divide by the hypotenuse, in this case, it's a. Now if you have trouble seeing where those came from, feel free to break your triangle up into the left side and right side triangles. They're both going to have h as their height. They are both right triangles. And the important sides are going to be angle B, angle A on the left triangle, and then recognizing that the hypotenusi are B on the left and A on the right. That might make it a little bit easier for you to see where these relationships come from if using the same triangle for both is confusing. Okay, let's take a look at these algebraically somewhat. And what I'd like you to notice is that both of these have the letter h in them. I could rearrange these, the top one by multiplying both sides by b, to produce something that's kind of interesting. I'm going to draw an arrow down here so I know where it goes. B times sine of angle A, and I have a times b divided by b, so that's going to cancel down to 1, equals h. If I do a similar operation on my second equation, multiply both sides by a, canceling to 1 on the right side, I end up with a times the sine of b also equals h. We know that if I have two quantities that both equal a third quantity, in this case b sine a and a sine b, both equal h. By the transitive property, these two quantities, the first two, b sine a and a sine b, must be equal. With a little bit more quick algebra work, I can divide both sides by AB, and that's going to leave me with the opposite sides and angles in the same parts. So here I have sine A divided by A is equal to sine B divided by B. Since we just chose this kind of arbitrarily as the orientation of our triangle, I hope you can imagine that the same would be true sine C divided by the length C. And we have our law of sines. Let's look at an application of this to help us understand a little bit better.